All right, in 9.2a, we're going to look at how do you actually do a significance test for a population proportion. All right, so several questions we're going to answer with this slide. Okay, first thing, what are the three conditions for conducting a significance test for a population proportion? There's three of them, and they should look a little familiar from our chapter on confidence intervals. So let's look at this. So the first condition to do a test is the sample random? Did it come from a well-designed sampling or a randomly assigned experiment? You're looking for that wording in the question. The second thing is the sample independent? Does it meet the 10% rule? Remember, the sample has to be less than or equal to 10% of the population. And then thirdly is the large counts test. And remember, with large counts tests, we're looking to see if the sampling distribution of the sample proportions is approximately normal in shape. And the way to check that is our large counts test. So it's n times p naught greater than or equal to 10, and then n times the complement of p naught has to be greater than or equal to 10. Now what's different here? Well, p naught is the p-value defined in your null hypothesis. Okay, so whatever they give you in the question, that's the p-value you're using right here. And it's really just the population parameter you're testing. Now, how are these different than the conditions for constructing a confidence interval? This is where it's different. In a confidence interval, we don't know what p naught is. All we have is the sample proportion, or p hat. So this is the big difference right here. And then third question is, what's a test statistic, and what does it measure, and is it on the formula sheet? Well, it measures how far a sample statistic diverges from the null hypothesis if the null is true. All right? And we're going to use two test statistics in this course, a z statistic and a t statistic. Okay, we've calculated these before, but it's either going to be z or t, and I'll show you when to use which one. Now, as far as on this formula chart, this is what's on the formula chart. It's just a generic formula. It's not z equals or t equals, right? But whether z or t, you're going to use the same idea. It's the statistic minus the parameter you're testing divided by the standard error of the statistic. Now, these look different whether it's proportions or means, so we'll dive into this more. So as we do a test, we're going to do 4 steps. And here's what's required for each step. First is the state step. And you're telling me what's the hypothesis you want to test and at what significance level. And you also want to make sure that you define the parameter. Tell me what p represents, the proportion of what. Define the parameters in the context of the question. Number 2 is the plan step. To identify the appropriate inference method and check the conditions, okay? Just like we did with confidence intervals. We had to say it was a 1 proportion confidence interval, or in this case, a 1 proportion z-test. And check the conditions that we talked about, the 3 conditions. Step 3, draw a picture. If the conditions are met, perform the appropriate calculations. That means find the test statistic and find the p-value for the area under the curve. I will model this for you in future slides. Hold on. And then last step is conclude. Make a conclusion about the hypothesis, reject it or fail to reject it, and you make it in the context of the question. All right, so let's get more specific. Which test statistic do we use to test a population proportion? Well, it's the z statistic. All right, and we take this sample percentage that we got, subtract it from the null percentage or the parameter of the population, and we divide it by this guy. This is the standard error of our statistic. We always do the calculations assuming that the null is true, meaning we use p naught in the standard error down here, not p hat. Okay? This is different than confidence intervals. In confidence intervals, all we had to use was p hat. But now that we're doing a significance test, we know what the claim is, so we use that value in the standard error. Is it on the formula sheet? Well, you can see it's not. It looks like this on the formula sheet right here. So your job is to put in the p hat minus the parameter divided by the standard error. Okay? All right, so remember there's 3 kinds of tests we're doing, and it all depends on the alternative hypothesis and what inequality we use. So first of all, if we used a greater than sign in our alternative, then we're doing a right-tailed test, and our z value should be a positive number. If if our inequality is a less than, then it's a left-tailed test. And usually this would be a negative value right here. And then lastly, what if it's a not equals to? Remember, that's called a two-tailed test, and we'll have two z values. We'll calculate one and then we'll find the other. It's either we find the negative and we make it positive or vice versa. All right, so let's try one of these tests. Just baby step our way through it. So according to an article in the San Gabriel Valley Tribune in 2003, most people are kissing the right way. That is, according to the study, the majority of couples prefer to tilt their heads to the right when kissing. In the study, a researcher observed a random sample of 124 kissing couples, found that 83 out of the 124 of the couples tilted to the right. Is this convincing evidence that the couples really do prefer to kiss the right way? Okay, so anytime you see this, is this convincing evidence? That's your clue that you're doing a four-step process, okay? State step, remember we define what we're testing. We want to test the following hypothesis at alpha equals 0.05 significance level, okay? You don't have to write significance level. If you put alpha equals, that's fine. Now, we want to know, all it says is majority as far as numbers, right? Majority. So remember, majority is going to refer to more than 50%, okay? So it's percent, so it's going to be P for my parameter. So the null is that P is equal to 50%. The alternative is that it's greater than 50%, because they think it's greater than. So also remember, if you're not sure, like on this, we think the majority is obviously going to be a greater than 50%, so that has to be alternative. But what about the null? Well, the null always has to have an equal sign with it. Okay, so if you're clear on the inequality of the alternative, just change it to an equal sign for the null. And the last thing here is to define what P represents. It's the true proportion of right tilting couples. All right, so now we need to dive deeper. For the plan step, we're going to need some more evidence from our question. So first of all, notice the sample size is 124 couples, and 83 out of the 124 tilted to the right. So this is the p hat value. Okay, it's x over n is sample. How many out of a sample tilted to the right? So that would be 83 couples. These values are going to be very important as we move into the plan step, so keep those in mind. Okay, on the plan step, we are going to perform a one sample z-test for P if the conditions are met. So then I run through my conditions. Okay, they said the sample was 124 randomly selected couples. Then I check the 10% condition. Is 124 less than 10% of all couples in the population? I would think so, probably so. I just show that it's true. So then, assuming that the null is 0.5, since we said that in our null hypothesis, we can do the large counts test. So we do n, 124 times 0.5, and then n times 1 minus 0.5. Both of them come out to be 62, which is greater than 10. This tells us that the sampling distribution of the sample proportions will be approximately normal, and we can proceed with the normal distribution and z calculations. Okay, so we've done state, we've done plan, let's do this thing. So, referencing what the question told me, the null was 0.5, the p hat was 83 out of 124, which gives me 0.669, right? I use these values then in my z statistic calculation, p hat minus p naught divided by p naught times 1 minus p naught divided by n, take the square root of that, and I get a z-score of 3.76. Then I draw my picture. 0 is the center because we standardized it. 3.76 is way over here to the right, and I'm looking for the area on the right. Remember, our alternative is greater than 50%, so it's a right-tailed test. So to find this area, I'm going to use the norm CDF function in my calculator. My lower boundary is 0.376, upper is like 10,000. Mu is 0, sigma is 1. The reason for that is because I have converted it to a z-score. It gives me a p-value of 0.0001. Now, I can use that value in my conclusion to make a decision. So, I start off by connecting the p-value I calculated to the alpha. So because the p-value, 0.001, is less than 0.05, remember if the p is low, we reject the we reject the null hypothesis. There is convincing evidence that, now I restate my alternative hypothesis, that more than half of the couples prefer to tilt right when kissing. All right,